Last class we discussed octet rule. So today we can see the drawbacks of octet rule. What are the failures of octet rule or the limitations of octet rule? The first one is incomplete octet of the central atom. Octet means 8 electrons. Incomplete octet means we can see compounds in which the central atoms, they are not having 8 electrons in their outermost orbit. For example, here you can see LiCl. Here lithium is getting only 2 electrons in the outermost shell. Chlorine has 8, but lithium has only 2 electrons. BeH2, beryllium hydride. Beryllium has only 4 electrons in its outermost shell. Hydrogen has only 2 electrons. BCl3, boron has only 6 electrons. So in all these cases, the octet is incomplete. Here instead of 8, only 2. Here instead of 8, only 4. Here instead of 8, only 6. But even then, the compounds exist and they are stable also. The second case, odd electron molecule, octet 8, that is an even number. But we can find out compounds which contain odd number of electrons. For example, nitric oxide. Nitric oxide has an unpaired electron. So, odd number of electrons. Nitrogen dioxide, NO2 also has an unpaired electron. So, here also the octet rule is not satisfied. An odd number electron. That means there will be an unpaired electron. If all the electrons are paired, that will give stability. But if there is an unpaired electron, that is against octet rule. In NO and NO2, there is unpaired electron. And the next one, expanded octet. It is the opposite case of the first one, incomplete octet. Expanded octet means in some compounds we can see central atoms with more than 8 electrons. Central atom with more than 8 electrons. That is expanded octet. Here you can see examples. PF5. Count 1, 2, 3, 4, 5. 5 into 10. Around phosphorus, there are 10 electrons in the outermost shell. 10 electrons, SF6. 1, 2, 3, 4, 5, 6. 6 into 12 electrons. Instead of 8, you can see here 12 electrons in the valence shell of sulfur. Here 5 electrons in the valence shell of phosphorus. Expanded octet. So again, remember which are the drawbacks that we mentioned here. First one, incomplete octet. Second one, odd electron molecules. Third one, expanded octet. All these are against octet rule. There are many other drawbacks. We can continue. Which are the other drawbacks? In the case of compounds, the octet rule is based on the inertness of noble gas. The octet rule is based on the inertness of noble gases. But now we know some noble gases react to form compounds. For example, xenon. Xenon can form many compounds. HCF2, HCF4, HCO3, such many compounds are possible. So it was based on the inertness of noble gases, but now it is proved even noble gases will react If this law was true, then noble gas will not react. No need to react. But if it is reacting, that is a failure. This theory does not account for the shape of molecule. From this theory, it is not possible to identify what is the shape of the molecule. There is nothing about the shapes of the molecules. It does not explain the relative stability of molecules or the energy of a molecule. Which one is more stable? That is not explained in octet rule. That is a failure. So we can identify such a number of failures for octet rule. The first three is more important, and these three are also important. You can notify the problems or defects of octet rule. Okay, now a little more things about the ionic or covalent bond. I told you ionic bond or covalent bond is formed by, ionic bond is formed by, not covalent bond, ionic bond or electrovalent bond. Ionic bond is formed by complete transfer of electron or electrons from one atom to the other. Complete transfer of electron. When we think about this complete transfer, it is not a simple process, transfer of electron from one atom to the other. If you want to transfer electrons, you have to overcome the attractive force from the nucleus. If A is donating electron, we have to supply energy to overcome the attractive force of nucleus. That is ionization enthalpy. But if you want to call it as ionization enthalpy, the atom A should be in the gaseous state and in the isolated state. That should be in the gaseous state and also should be in the isolated state. If you want to convert a solid atom to a gaseous atom, you have to supply sublimation energy. What is sublimation? Conversion of a solid substance directly into gaseous state without going through the liquid state. That is sublimation. So for the conversion of a solid atom to gaseous atom, sublimation energy is needed. We need isolated atoms. If two atoms combine together, we have to supply dissociation energy. So dissociation energy is needed. Then if you want to add an electron, electron gain enthalpy, that may be negative or positive. There is electron gain enthalpy. Electron gain enthalpy has a role. Sublimation energy, ionization enthalpy, dissociation, bond dissociation enthalpy, electron gain enthalpy, such a number of energy factors or energy changes are involved. After the formation of positive and negative ion, when they combine together, it is going to a highly stable state. As a result, what happens? Huge amount of energy will be released, and that energy is lattice enthalpy. Lattice enthalpy. So what are the energy changes associated with the formation of an ionic compound? Ionization enthalpy, enthalpy of sublimation, bond dissociation enthalpy, electron gain enthalpy, and lattice enthalpy. Lattice enthalpy is defined as the energy required to completely separate 1 mole of a solid ionic compound into gaseous constituent ions. The lattice enthalpy of an ionic compound is defined as the energy required to completely separate. Energy required to completely separate 1 mole of a solid ionic compound into gaseous constituent ions. So you have to listen that point. 1 mole of a solid ionic compound. Solid ionic compound into gaseous, into gaseous constituent ions. That is lattice enthalpy. So it is a very important term, lattice enthalpy. It has a major role in the properties of ionic compounds. So a very important term, lattice enthalpy. You have to study it well. So we can conclude a qualitative measure of the stability of an ionic compound is provided by its enthalpy of lattice formation and not simply by achieving octet of electrons around the ionic species in the gaseous state. In many cases, we observe the failure of octet rule. So the octet is not only the reason for the stability or reactivity of the atoms. In the case of ionic compound, there is another important factor, that is lattice enthalpy or enthalpy of lattice formation. So that also plays an important role in the formation of compounds. This is the conclusion from the involvement of different energies in the formation of ionic bond. Surely there is stability due to octet in the outermost orbit. But we cannot consider it as the only one reason for the stability. There are other factors. In the case of ionic compound, that factor is lattice enthalpy or enthalpy of lattice formation. I think it is clear to you. Now we have to study the bond parameters. However, there is bond formation. When atoms combine together, there is bond formation. When atoms combine together to form molecule, there is bond formation. And if there is bond formation, we can identify some bond parameters. We have to study that bond parameters. First one is bond length. Bond length is defined as the distance between the nuclei of bonded atoms, distance between the nuclei of bonded atoms. What is bond length? It is defined as the distance between the nuclei of bonded atoms. Here you can see two atoms combined together. This is the nuclei of first atom, this is the nuclei of second atom. And you can see 198 picometer is the distance between the nuclei of two bonded atoms. And that 198 picometer is considered as the bond length. 198 picometer is considered as the bond length. And here these two molecules are combined. But here these two atoms are not close to each other. However, in that case also, the bond length is considered as the distance between the nuclei of two bonded atoms. So did you understand what is bond length? The van der Waals radius that we already discussed in the third chapter. Van der Waals radius, covalent radius, and metallic radius. So I am not repeating it here. I think it may be clear to you. Okay, the next one is bond angle. It was a question for this year improvement examination. What is bond angle? That was the question. It is defined as the angle between the orbitals containing bonding electron pairs around the central atom in a molecule or complex ion. It is defined as the angle between orbitals containing bonding electron pair. Angles between orbitals containing bonding electron pair around the central atom in a molecule or complex ion. If you feel any difficulty to write this one, just to draw an example and show what is bond angle. So you can see the angle between two adjacent bonds in a molecule. Simply we can say it is the angle between two adjacent bonds in a molecule. Here H2O is given. What is the bond angle here? 104.5 degree. HOH bond angle in water can be represented in this way. So if you have a question bond angle, in a simple sense, what you can write, it is the angle between two adjacent bonds in a molecule. Then you represent H2O and show the bond angle in H2O. HOH bond angle, 104.5 degree. It is a simple concept, but when it is asked as a question, you should be able to write it. That is important. Okay, bond enthalpy, another term, bond enthalpy. Already we mentioned bond enthalpy. What is bond enthalpy? It is the energy required to break a particular type of bond. And the quantity also important. 1 mole of a particular type of bond. So what is bond enthalpy? It is defined as the amount of energy required to break 1 mole of bonds of a particular type between two atoms. 1 mole of a bond, 1 mole of bonds of a particular type between two atoms in a gaseous state. There also the condition gaseous state. Energy required to break the atoms of a molecule or the bonds between the atoms of a molecule in its gaseous state. That is bond enthalpy. Is it clear? Bond enthalpy is defined as the amount of energy required to break 1 mole of bonds. Energy required to break 1 mole of a bond, 1 mole of bond of a particular type. 1 mole of a bond of particular type between two atoms in gaseous state. What is meant by mean or average bond enthalpy? Mean or average bond enthalpy. With the help of an example, we can explain it. In H2O, O is bonded to two hydrogen atoms, isn't it? In H2O, oxygen is bonded to two hydrogen atoms. There are two OH bonds, and the energy required to break the first OH bond will be different from the energy required to break the second OH bond. If you want to break the first OH bond, you have to supply more amount of energy because that is a stable molecule. After the breaking of one OH bond, the molecule will be unstable. So for breaking the second OH bond, lower energy is needed. So here you can see H2O dissociated into H plus OH. One OH bond is remaining, our OH bond is dissociated. And the energy required for the breaking of this bond, 502 kilojoule per mole. When it breaks the second OH, H plus O, the energy is required is 427 kilojoule per mole. So what is average bond enthalpy? 502 plus 427 divided by 2. That is the average bond enthalpy of OH bond in H2O. Did you understand? In case of more than one similar bonds, we have to take its average. Here two OH bonds. So when you take the average, you will get the bond enthalpy. Average bond enthalpy of the two bonds. If you measure it separately, that will be different. Okay, now the next concept is resonance. What is resonance? If you listen carefully, if it is impossible to explain the properties of a compound with a single structure, if it is difficult to explain the properties of a compound with a single structure, we will use several structures to explain the properties of the compound. We can use several structures, means more than one structure, to explain the properties of the compound. That is known as resonance. Example, ozone. It is not possible to explain properties of ozone with a single structure. The reason, if you measure the bond length of O bonds in ozone using advanced spectroscopic method, we can identify it is 128 picometer. And if you are using this structure, this bond has 121 picometer length and this bond has 148 picometer length. Is it possible to explain this property with the help of this structure? No. Here two types of bonds are there. 121 picometer and 148 picometer. But advanced spectroscopic measurement showed that it has only 128 picometer length. How will you explain it? Or how will you explain the property? Here, it is not possible to explain the property with a single structure. So we are using another structure. Here, this double bond is shifted to this position. You can see. Now, this bond length is 121 picometer and this bond length is 148 picometer. So here, in the first case, it was 148. Now it is 121. We can take the average. Here also we can take the average. So instead of two bonds, you will get similar bonds. Two different bonds means two bonds with the different bond lengths. You'll get two bonds with the same bond length. So the structures using to explain the property is known as contributing structures or canonical structures or resonating structures. Here structure one is a contributes to the exact structure, a contributing structure or a resonating structure or canonical structure. Two, also a resonating structure or canonical structure or contributing structure. It is not the exact structure and it is not the exact structure. The exact structure is in between these two. It is there we can observe fast conversion of this structure to this structure to this one, fast in conversions. So the exact structure, we cannot say what is the exact structure that is in between the contributing structures 1 and 2. Approximately, we can represent the exact structure in this way. And this exact structure is known as resonance hybrid. Resonance hybrid. Okay, all these things are explained here. If a single Lewis structure is not enough to explain all the properties of a compound, more structures with similar energy and shape can be used. This concept is known as resonance. The different structures using to explain the properties are known as canonical structures or contributing structures or resonance structures. The actual structure is known as resonance hybrid. As the number of resonance structures increases, stability of the molecule increases. If you want many such structures to explain the properties of a single compound, its stability will increase. Its stability will increase. So stability increases with increase in number of contributing structures or resonance structures. Resonance stabilizes the molecule as the energy of the resonance hybrid is less than the energy of any single canonical structure. Resonance stabilizes the molecule. As the number of resonance structures increases, stability increases. the energy of the resonance hybrid will be always less than any of the canonical structure. So resonance stabilizes a molecule. So it is enough for today. All of you watch the video, write notes, and submit the assignments in time. Okay.